Welcome to section 6 of the SEMTRAIN Professional Engineering, Electrical Engineering Power Exam Prep uh, on demand course. This section is short, about 23 slides, and this particular section deals with the topic of power factor and power factor correction. The reason for this topic being short is this is specific um, coverage of the power factor topic, but power factor will also get come up and get introduced and be covered in other sections yet to come. So this is just the beginning of it, you might say, or just a specific coverage of power factor. For example, when we do motors, you'll see power factor crop up there as well. And then when you do your PPI problems, you'll see the power factor crop up there as well. Okay, so let's go ahead and switch to our slideshow and activate our pointer. And there we go. All right. So you've already heard me mention the term power factor a few times. I think I've mentioned in one of the foregoing segments that power factor can be defined two ways. It can be defined as a ratio of real power divided by apparent power, or it can be defined mathematically as the cosine of the angular difference between the voltage and current. Angular difference between or difference between the voltage angle and the current angle. Cosine of that. So we can calculate the power factor either way. The first definition of power factor, where power factor is defined as real power divided by apparent power, or kilowatts divided by kVA, or watts divided by VA. That definition, has a special meaning in that it basically represents or foretells the how efficiently you're using AC power in your operation. So therefore, power factors multiplied by the decimal values multiplied by 100 to represent the power factor in percent. So the higher the percentage, the higher the efficiency, of course, the maximum being 100% when P becomes equal to S. That happens when the power factor is 1.0. So that's a little bit of introduction about the power factor. And with that, you see this slide and the next one depicting two different scenarios. One scenario is that of a leading power factor, and the other one that'll come up in the next slide, that we'll visit in the next slide, is the scenario that involves the a lagging current. So what we'll do actually is look at the lagging current scenario first, and so that's this right here. And so we've already defined how you calculate the power factor, but power factor can be leading or lagging depending upon whether the current is lagging behind the voltage or leading the voltage. So when the current is lagging behind the voltage, the power factor is the lagging power factor. And that occurs when you have a predominantly reactive inductive system. When you have a predominance of inductive reactance in the system. You walk into a large industrial plant, you're going to basically find a predominance of inductive reactance. You have motors, you have transformers, large motors, large transformers, not as many capacitors. So you end up being those large industrial plants, large commercial facilities, large institutional buildings, you typically will see that they have a predominantly inductive impedance, and therefore the current always lags behind the voltage. And that representation of a current lagging behind the voltage is shown right here in a graphical form. So you see that the current represented by the blue line is rising above the x-axis after the voltage rises, and therefore the current is said to be lagging by how much? By a factor of theta. And so once again, a quick review, something I mentioned early on in one of the early segments. You're plotting along the x-axis, you can plot time or angle. So angle and time are interchangeable. So that's why we're saying that if a current is lagging behind the voltage time-wise, it's also lagging behind the voltage in angle. And that angular difference between the voltage, the cosine of the angular difference between the voltage and current waveforms is the power factor, which is also equal to P divided by S. So that's essentially what we're talking about here. And as far as when you have a lagging power factor, how do you remedy that? Because the current is lagging behind the voltage due to the fact that there's an abundance of inductive reactance, you counter it by introducing capacitive reactance. And that's why one of the common corrective measures for improving power factor in a typical industrial commercial environment is through the addition of capacitors, through the addition of X sub C to offset the X sub L. And if you, we're going through some basics here and not working any problems yet, but any of this information I'm presenting could easily show up in form of an actual problem. And so let me activate a different color pen here. Okay, so you remember that we define overall impedance in a system Z, okay, as being equal to the R in the system plus J X sub L, where J X sub L represents really Z sub C, minus J X sub C. Okay, so that's how we define overall impedance. And let me activate my pointer back up. So that kind of tells us that if your power factor is poor because of too much X sub L, then as you add X sub C, what is minus Jx sub C doing? It's offsetting plus Jx sub L. So that's another way of viewing why and how additional capacitors remedies poor power factors. So that's one thing to remember. And then we can look at the whole power factor business vectorially as well. And that's shown up here. So imagine yourself, up here, looking down at this, looking down at these vectors. And which vectors are we talking about here? The current vector, voltage vector, and basically the current and voltage vector, because that's what we're talking about here, the difference between current and voltage, angles representing the power factor. And in this case, the difference between the current vector, the angle between the current vector and the voltage vector is the power factor angle. If that were 30 degrees, cosine of 30 is 0.866. The power factor would be 0.866 times 100, or 86.6%. So that's essentially what we're looking at. Current is lagging behind the voltage. If you view these vectors rotating by counterclockwise, you will see voltage go by first and then current, and hence you say that the current is lagging behind the voltage. And so, and I'm kind of explaining anecdotally, and kind of graphically and physically this whole concept of power factor. Uh, and I'm with the hope that as you understand the physical aspects of power factor, you'll be able to analyze, understand any power factor question you encounter in the exam easily, and immerse yourself in the problem and see the problem and analyze it quickly, and solve it quickly. So anyway, so let's just imagine a situation. You've got a lot of inductive reactance in a system, in a building, in a facility, and that is causing the current to lag behind the voltage by 30 degrees. So the power factor currently is 0.866 or 86.6%. And your charter is to correct that power factor to 100% unity, utopian power factor value. Although in real life you rarely attempt to go after a 1.0 power factor, you improve it to a reasonable level. There are economics involved. There's you could say engineering economics involved, energy economics involved, but we're not going to get into all of that here now. But so bottom line, let's just say that's what it is. The current is 30 degrees behind the voltage, and therefore the power factor is 86.6%. And your objective is to improve the power factor to 1.0 or 100%. To do that, you start injecting capacitance. You start installing fixed capacitors. And as you do that, one capacitor at a time, the current gets closer and closer and closer to the voltage until it overlaps with the voltage. And when it does, what is the power factor now? The angular difference between current and voltage is 0. Cosine of 0 is 1. Power factor is 100%. So you've met your objective. Only if you could freeze everything there forever and ever. Well, now let's assume that inductive load that was causing the current to lag behind the voltage is turned off, shut off, taken out of the system. Whether it's temporarily or permanently, doesn't matter. When the inductance drops out, the inductance that was causing the current to drop fall behind the voltage, when that inductance disappears, that's as if you've overdosed the system with the equivalent amount of capacitive reactance. So what will theoretically happen is that the current will go past the voltage by 30 degrees. But yet, the angular difference between the current and the voltage, and let me go ahead and draw that real quickly. So we're kind of working a problem with some examples of practical situations. And so in other words, now we're saying that the current is up here. It is now well ahead of the voltage by the same amount because the whole inductance just disappeared. We're just kind of coming up with using a hypothetical scenario to understand this concept better. So anyway, you got now the current is surpassed the voltage by 30 degrees, but cosine doesn't care whether the angular difference is negative or positive. Either way, even now, when you take the cosine of 30 degrees, you'll still end up with a 0.866 or 86.6% power factor. So power factor, you had achieved unity, perfect utopian scenario, but then as the load drops out or dropped out, now the power factor, now your system is overdosed with capacitance, and the power factor back down to 86.6%. And to avoid that, sometimes you use automatic power factor correcting cap banks. Power factor, the capacitors are connected in the circuit automatically, injected into the system when the power factor drops. When the power factor goes back up, those capacitors are taken out, and so you're automatically monitoring the power factor and responding to it by injecting or removing capacitors automatically using PLCs or whatnot. So anyway, that's a way of looking at power factor. Another way of looking at power factor and power factor related problems, challenges, physically, practically, and also theoretically, mathematically. Now, what we just explained, this correction and remediation of power factor, can also be accomplished by using a synchronous motor. And when you get into the motors segment, you'll see that we will actually talk about how power factor is corrected using synchronous motors. And we'll illustrate that through numerical problems. You'll work some problems like that in the PPI EPRP book. You'll work problems like that in the NCE's sample exam booklet or sample exams. Okay, that's essentially what we wanted to cover on this slide, and then the slide, as far as the slide I skipped, that essentially shows you. And let's just talk about it just briefly, because you could encounter a problem that involves this type of understanding. So when you have too much capacitance in the circuit, vectorially, it would amount to basically current leading the voltage by a certain degree, a certain amount, or certain angle. And so if this were 30 degrees, current is leading the voltage by 30 degrees, or so let's just say 45, just change the angle a little bit. If this were 45 degrees, cosine of 45 would be 0.707 or 70.7% power factor. And if you had a situation like that, which is what happens with long runs of transmission lines, how do you correct that situation? You do the opposite. You put in inductance into the system to correct the power factor. That's what power companies do on those long runs of transmission lines where they build up a lot of capacitance over those long runs and capacitive reactance, which is what deteriorates the power factor there. Totally opposite challenge than what you face on the consumer side of the fence. Also note that when you look at pure capacitance, it's represented by this negative vector right here, which is minus Jx sub c. Just like in the other scenario, pure inductance is shown by this upward directed vector right here, which is plus Jx sub L. Just a quick review refresher. Okay, so before we cover this slide, let me just back up a little bit again and mention something else very, very quickly to perhaps help you understand power factor a little more if this happens to be one of your weak suits. Often, people sometimes will understand power factor mathematically, but physically struggle with, what is really going on with power factor correction physically. Well, physically, think of inductors, as devices that, or inductive reactance as devices or systems or entities that basically are demanding this energy. We know inductors store energy. It's 1/2 Li squared. And so when you have inductance in the system, where do they get this energy that they need, that 1/2 Li squared? Well, they borrow it essentially from utility. It's coming from the S. By increasing the Q, the S rises, and so it's actually being borrowed from utility, and that's why utility companies do not want don't look upon so kindly when your power factor drops due to inductive reactance. But when you put capacitors in there, and if you're wondering how does the capacitor really remedy poor power factor, well, capacitor is an energy storage device as well, 1/2 CV squared, and so the energy you store in a capacitor, it becomes a repository, a bank of energy that your inductors can borrow from. So instead of getting the energy from the utility company, the energy is being borrowed from the capacitor, and therefore when the utility company looks at you, and you're not demanding any additional S from the parent power from the utility company, the utility company sees your power factor as being Good. And so that's physically what's going on. That's just a little physical explanation of what happens with poor power factors and remediation of poor power factor using power factor correcting capacitors. So this particular slide, I'm sharing with you a formula that helps you do per phase analysis or calculation of how much capacitance you need to add into a system to improve the power factor. And so what does power factor improvement really mean or amount to? It amounts to net reduction in reactive power, Q. Remember that that S, overall apparent power S, is equal to P plus J Q. And so when power factor, and what I'm explaining here, I would advise that you listen to it, and if power factor topic is a weak suit for you, listen to it carefully, and then if it doesn't really comport with your thinking, to listen to it again, and then try to write it down and practice it and turn it into an equation and play with it a little bit. So when your power factor is poor, it's because of too much inductive reactance, which drives up the Q, the reactive power Q, the VARs. And when Q goes up, the S goes up. The real P does not change. The real power, the torque required by the load, whether it's pump requiring that torque, or it's a conveyor belt you're moving sand on, or whatever, that is not changing. That stays constant. That's one way to look at it. So when you add a lot of inductance in the system, Q goes up and S goes up. Well, power factor is defined as the ratio of P over S. So if P is staying constant and S is going up because of too much inductive reactance, what's happening to the power factor? It's going down because the ratio of P over S is going down. So that's another way of looking at the dynamics of power factor. And if you understand the dynamics of how power factor goes down, you can better understand the dynamics of how you remedy it. And can better understand power factor related problems and work them easily. And you can pretty much rest assured you're going to have multiple power factor related problems. They may not be exclusively power factor type of problems. They may be problems that entail complete understanding of power factor. So that's why this topic is of high value, even though we don't have many slides injected in here for it, specifically in this section. So anyway, so bottom line, when you correct power factor, if you're not aiming, as is the case practically speaking in practical circumstances, you don't look to eliminate all the or improve the power factor to utopian 1.0, you typically, practically speaking, you try to lower the Q from a higher undesirable level to a lower acceptable level. So therefore, you're going from a higher Q value to a lower Q value. So if your objective is stated as reduction of Q, or as part of your analysis, you've gotten to the point where you know how much reduction in Q is needed to improve the power factor by the desired amount, then you take the difference in the old higher Q and the lower Q, which gives you the net change in Q you're trying to affect. You take that delta Q and divide it by 2 pi frequency and voltage RMS squared. And that'll give you the capacitance in farads. That's how much capacitance you need to add on per phase basis. Everything is per phase in order to remedy and improve the power factor such that you're able to reduce the Q in the system by this amount. And that is the reason, actually, when you order capacitors, for power factor correction type of applications or examples of situations, you don't order typically those power factor correcting caps by infrareds. You don't specify infrareds. You specify them in Q. So if you want to reduce the Q by a certain amount, you order that much of the capacitive Q in VARs. And what is Q measured in? In VARs, kVARs. So you order basically 10 kVARs or 20 kVARs worth of capacitance for power factor correction purposes. So that's, I think you'll find this explanation important in understanding what happens in power factor, with power factor improvement, power factor remediation, and when you are trying to grapple with the situation of a poor power factor. And when you understand all of this properly, then the whole concept of power factor, you're able to analyze questions related to power factor easily and so forth. Okay, so we have a power factor correction example or problem. We have 100 kVA, and as soon as you read 100 kVA, that should pop up in your head at this point is S. So given S, the load is expressed in S value, the apparent power. It's operating currently at 0.8 power factor, lagging. How much capacitance is required to correct the power factor to 0.95, lagging? So multiple ways of scaling this, multiple ways of doing this problem. And one of the ways could be that you basically examine what your Q value is at the existing lower power factor of 0.8, then examine your Q value at the 0.95 lagging power factor, and the difference of those two Q values can be used in that very equation that we just covered, and you can assess the amount of capacitance needed. So, or you could apply a different method, and which is what you're seeing here. I do encourage you to try the method I just mentioned, the alternate method, but here we're going to follow the solution that is given specifically, the approach that's given here in the slides. Initially the approach is the same as I just got ready to describe to you. You do look at, you take the 100 kVA S value, and you fully analyze it in P and Q form at the 0.8 power factor, lagging power factor. So in other words, our cosine of this gives you 36.9, and that's the power factor angle at 0.8 power factor. So in other words, you are able to now draw the power factor triangle at the 0.8 power factor, in the 0.8 power factor situation. And we know what the S is. We know what this angle is. S cosine S times the cosine of 36.9 would essentially give you the real power, which is essentially just 0.8 times 100, which is essentially 80, and that would give you that's 80 kilowatts. And the information we're deriving here, calculating here, it goes beyond the scope of what's really needed here. But I encourage you to do all of it. This will be a very good exercise for you to fully understand power factor type of problems, and to be able to slice and dice power factor type of problems from different angles to address different objectives and so forth. So we took the S and converted it into a power factor triangle by assigning this angle up here after calculating the power factor angle, and then derived the real power of 80 kilowatts. Then if that's the real power, what is the Q value? It'll be S times sine of this angle, which gives you this, and the Q value of 60 kVA. So you see how you can do it. You got the initial Q value here with the 0.8 power factor, but then you do the second set of calculations, and that would be for a power factor of 0.95. and the arc cosine of that basically gives you 18 degrees right here. 18 degrees, 18.2 degrees. So, so our new triangle will have 18.2 degrees as the power factor angle, and as we learned earlier, the P stays the same. So, you have the base of the triangle, you have this angle, and you can use, you can essentially take the cosine of this. The cosine of this angle would be equal to P over S. And therefore S would be equal to the 0.8 divided by the cosine of this angle, and so that way you can end up with defining S value, and which will indeed be different. It'll with the 0.95 lagging power factor, and I encourage you to calculate that as a part of additional practice and honing your skills. You will see that when you find the S value with this 0.9 power factor, that it is less than the S value we had up here, because the power factor is improved. The higher the power factor, the lower the S. The lower the power factor, the greater the S. And again, I encourage you to prove this mathematically by using different angles or power factor values and trying it out. So anyway, so this is your real value. The real power doesn't change. So now the question is, what's the new Q? Well, there you can use tangent. Tangent of 18.2 is equal to Q over P. So, so Q would be equal to P times the tangent of this. So there it is. P times tangent of 18.2 gives you the desired Q. So now you have the desired Q. You know what the initial Q is right here. Okay, 60. The difference between those two is what you're going to order. That'll be the size of the kVAR size of the cap bank you're going to order to achieve this correction of power factor from 0.8 to 0.95 lagging. Or, as I said earlier, you know, I would encourage you to, once you've found the two Qs right here, take this problem a step further. And yeah, actually we do some of that here, but I encourage you to, in this problem, take this problem a step beyond this, and take this delta Q, plug it in this equation, delta Q divided by 2 pi 60 hertz, and the voltage, perfect, but it has to be phase voltage if that's available, and that'll give you the C value. And in our case, I'm not sure if the voltage is given. No, it's not. Unfortunately, you can't calculate the C value because the voltage is not given. But if the voltage were given, you could use that formula that we that I just pointed to find the C value. And you know, questions like that would use this equation to find the C value are common. They show up commonly in the NCE type exam. And later on you'll see examples of problems where you can use this formula. I encourage you to test it out for yourself, and because it gives you a good shortcut. If capacitance is what you're trying to determine on per phase, how much you need to add to correct the power factor, you just use that canned equation to find the how much capacitance you need to add per phase to reduce the Q value or improve the power factor. And if you're wondering where in the world does this formula come from, well, it essentially comes from that equation, which essentially states that Q is equal to V squared over X sub C. The formula for calculation of Q, reactive power. Let me state it again. Q equals V squared over X sub C. And that formula is stated at multiple places in this course. You'll come across it. If you've not already seen it, you'll see it again later on in other sections. Okay, so So that's a little bit of going back and forth and showing you the value of that equation, and we just worked this particular problem on power factor. So let's move on. And problem number 2, we have 180 VA three-phase load. It's operating at a power factor of 0.56, rather poor power factor. Assuming Y configuration, the amount of per phase capacitance that must be added to correct the power factor to 1.0 would be what? So here we go from 0.562 to 1.0. And the question is how much per phase capacitance should be added to do that. So you would basically, in this case, need to determine the Q, the net Q, the change in Q. And once you know what the change in Q is, you can, that's one way to find the, and you use the Q and the VA. Well, Q is determined from the VA. And since the voltage is not given, you would not essentially be able to use that formula that I shared with you earlier a few slides ago, where Q1 minus, where you saw Q1 minus Q2 divided by 2 pi f V squared being equal to C, because the voltage is not given. So here, in order to find how much capacitance must be added per phase, you would need to focus on this S and breaking it down into the P and Q values. And there it is. And yeah, okay. So let's go back and read this question again. This question, my apologies, could be actually stated a little more clearly. Notice that after reading all the whole problem statement, it basically says how much, assuming Y configuration, the amount of per phase capacitance needed to be added is most nearly what? Well, when you read this, it seems to imply that you're actually trying to find the farads. But what we should do here, and we will reformat this question and say in parentheses in kVARs, because that's all you can find in the absence of voltage. All you can find is the kVARs correction, the amount of correction needed in kVARs. So and that's what we're doing here. So basically, you take your S and you convert it into the P and S values, or basically find the Q value by using this power factor, knowing that Q would be a sine of the power factor angle, and once you find the would be S times sine of the power factor angle, and power factor angle is 56.3 if you take the arc cosine of 0.56. So then you take the sine of that and multiply it with the S, and you would get the Q value, and that is 150 kVA. So if that is 150 kVA, then sorry, this is not kVA. This should be VARs. Okay, it's a typo. So let me go ahead and put an R up here. Okay, it's kVARs. All right, so it's kVARs. So the kVAR at 0.56 power factor is 150. The question is, how much kVARs do we need to add to make it unity power factor? And that answer would be an equivalent amount of minus J 150 kVARs. In other words, you would need to this total S, you would need to add minus J 150 kVARs to get rid of this completely, such that the power factor is 1.0. So therefore, the answer would be minus J 150 kVAR, or minus or 150 kVAR worth of capacitive reactance. Okay, so there's also a little issue here, and my apologies. There's also another typo up here. I forgot to add there's a K missing right here. So let's go ahead and add that. Okay, this is kVA, not VA. and there it is. It's correctly entered into this equation. Everything else is okay. It's just that we missed the k, and but the answer would be minus 150. And let's see here, and this k really ought to be up here to be absolutely correct. Okay. All right, and so this is an ancillary. And actually, let's see here. Um, let's see here. Yep. Okay. So that's basically the end of this problem with the information that's given. Now we go beyond and beyond that particular problem and try to actually see if we can find the C value. But to find the C value, we're going to have to assume or know what the voltage is. So and so that in this ancillary, we say that, okay, find the C value, assuming that, let's see in here, do we state what kind of circuit it was? No. We've not stated whether this is a Y or a delta. So therefore, in the ancillary, we're basically taking two different paths. We're trying to challenge ourselves and saying, okay, well, can we find the capacitance, per phase capacitance that must be added if the load is in delta configured versus if the load is Y configured, and if the voltage is 208 volts line to line. If the voltage if it's Y configured and the line to line voltage is 208, that divide this by square root of 3 and you'll get 120. The line to neutral voltage will be 120. Okay, so all right.